Okay, catalysis. So rates of chemical reactions can be controlled in several ways. We've looked at the effect of concentration. You increase the concentration, usually increase the rate. We looked at the effect of temperature. Most reactions, you increase the temperature, the reaction goes faster. But both of these have limits. There are situations where you can't increase the concentration, or you can't increase the temperature, or you want to slow things down and you can't reduce. So what do? Well, a catalyst can increase the rate without being consumed. And it does this by providing an alternate mechanism where that rate determining step has a lower activation energy, and so it occurs faster than in the original mechanism. So here we have that decomposition of ozone that we were just looking at. So in the uncatalyzed pathway, we have a transition state that occurs, and there's an activation energy for that. There's a catalyzed pathway where we have two transition states, but they each have a low activation energy, and so now the reaction occurs faster. So the uncatalyzed reaction occurs in one step. It's a single elementary step. O3 plus O makes 2 oxygen, but it's very slow. Chlorine atoms catalyze and make a different pathway. Yes?
Why do we want to...
Why do we want to destroy ozone?
Yeah.
We don't.
Okay. So are we just showing like how it happens?
Yes. So we're showing actually how chlorofluorocarbons cause the destruction of ozone. Yeah. No, we're not doing this on purpose. We are observing something that happens. Yeah, we're just observing something that happens. And this one is useful for several reasons. One of them is that people know about it and are concerned about it. Yeah.
Also, ozone is really harmful to human health. Well, that could be. It's not.
Yeah, so, ozone, it's a funny thing about ozone. Ozone is good in the upper atmosphere. It's great up there. Not so good down here, right? So here is the mechanism for the catalytic destruction of ozone by chlorine atoms. So a chlorine atom reacts with an ozone molecule and forms chlorine monoxide and an oxygen. The chlorine monoxide reacts with an oxygen atom and forms another chlorine and oxygen. So if we look at this overall reaction, the chlorine atoms disappear and the CLOs disappear, and we have O3 plus O forms 2 O2. Yes?
Okay, so I know that the chlorine is not supposed to be used up, but how does it stay atomic chlorine and not diatomic?
We'll get to that. For now, just believe me, it's chlorine atoms. Yeah. Yes, chlorine usually forms diatomic molecules, but there's other stuff going on up there. Yes?
So, since chlorine is in that portion of the first reaction and the second reaction is first step and the second step, does that make it a catalyst?
Yes. So, ClO is a reaction intermediate. It wasn't present initially. It's formed and destroyed. Chlorine is a catalyst. It was present initially. It's destroyed or affected some way and then recreated. And so that's how you can tell what's a catalyst and what is a reaction intermediate. So the activation energy for the rate limiting step in this one is much lower, and so the reaction occurs faster. The chlorine's not consumed. Yes?
So the third bullet, I think, doesn't
Yes, it does.
It's the radiation that keeps
Mhm.
ions.
So up in the atmosphere, chlorine gas gets hit by UV light from the sun, and that causes the chlorine atoms to dissociate. Yes. Which is also really the benefit of ozone, is that the ozone absorbs UV rays. And so that's why we need it up there, because it absorbs UV rays, and it makes oxygen and an oxygen atom, and then those make ozone again. But the chlorine messes it up.
So you say that CO is not consumed, but when you're talking, when you asked a question earlier, you said it's there, it gets destroyed, and then reforms later on.
Yeah, you could think of it as it being destroyed here, because I had chlorine atoms, and now I don't have chlorine atoms.
Right.
Well, the chlorine is occupied with the oxygen here.
It's not really like destroyed, it just turns into something else,
Yeah.
and then it goes back to
It's involved in the middle, but then at the end, we get the original thing back.
And that happens with all catalysts.
All catalysts. Yep.
So they should cancel out.
Right. If they're involved in a reaction intermediate, those reaction intermediates will cancel out. Yeah. I know your wheels are turning. I can almost hear them. Yeah. Anybody else have questions? Yeah.
So catalysts aren't represented in the overall reaction when you write it out?
Catalysts are not represented in the overall reaction. Yeah. So you've probably heard of catalytic converters. If you have a combustion engine, regular gasoline-powered car, you've got a catalytic converter in it. And what this does is the catalytic converter has a ceramic substrate in here with a catalyst such as platinum, rhodium, or palladium. And these metals catalyze a reaction that takes harmful exhaust compounds and creates less harmful compounds. So here we've got things like nitrogen monoxide and carbon monoxide coming out of the exhaust. And the catalytic converter converts those into nitrogen gas and carbon dioxide. And these are two normal components of air. It also helps to burn up any fuel fragments. So sometimes not all the fuel gets completely burned, and so you might have some fragments that get through. And so this fuel fragment will react with oxygen and form CO2 and H2O, and the catalyst in here also catalyzes that reaction. This reaction would occur on its own, but the rate is very slow. And so by catalyzing it, we can cause it to go quickly so that we can avoid putting NO and CO into the atmosphere from our cars. Carbon dioxide concentrations are of a concern, but they're not nearly as concerning as these other things. There are different types of catalysis, homogeneous and heterogeneous. In a homogeneous catalysis, we have the catalyst being in the same physical phase as the reactants. So they're all in the solid state, or all in the liquid state, or all in the gas state. So an example of this is the catalytic destruction of ozone. So we've got ozone and chlorine atoms, and they're both in the gas state. That's homogeneous. Heterogeneous catalysis is like in the catalytic converter, where the catalyst and the reactant molecules are in different phases. So here, the catalyst is on a solid surface, and the reactants are in the gas state. Yes?
Is it preferred, are either of those catalysts preferred?
So is one better than the other? They have advantages and disadvantages. So it depends on what you're trying to do, right? So if you're trying to catalyze the complete combustion of fuel and those other harmful pollutants, you want to have a solid state catalyst, because if it's in the gas state, it's going to float away with the rest of your exhaust, right? And so that's just not going to be that helpful. By having a solid, you can keep it in the muffler part of your car and make everything go past it and not lose it. Yeah. Any other questions? Okay, so this is interesting. And I encourage you to read this in the textbook as well. So there's this hole in the ozone layer that shows up in the spring every year. And when I was reviewing these slides last week, I was looking at this and thinking, May, September, wait, that's fall. Yeah, but this is the southern hemisphere. This is spring in the southern hemisphere. They're opposite of us, right? So most of the time, we have a fairly uniform ozone layer, and here blue is the less dense ozone. In September, over Antarctica, we see this big hole form. And the first time they observed this back in the 80s, they like freaked out. What the heck? We're going to, But then it fixed itself. And the next spring, it came back. And it fixed itself. And the next spring, it came back. It does this every spring. And it's really, really weird. So chlorine is the catalyst for the destruction of ozone. But chlorine is a gas, and it's uniformly spread throughout the atmosphere. So why does this happen over the South Pole? Why not everywhere? Well, the chlorine atoms from the chlorofluorocarbons get bound up in substances like ClO, and other compounds. And those compounds do not photodissociate into chlorine atoms, and so they don't catalyze the destruction of ozone. But these compounds get stuck. We get these polar stratospheric clouds. So you've got the clouds, and during the winter in Antarctica, no sunlight at all, right? Really, really cold. And so these clouds are frozen ice particles. The ice particles catalyze the release of chlorine from those compounds. And then in the spring, when the sunlight comes, there's all this chlorine that got released during the dark months, and the sun comes and photodissociates it, and then it destroys the ozone. It makes a big hole. And so that goes on for 6 to 8 weeks until all the ice in the clouds melts, which stops doing this and stops producing chlorine to destroy the ozone. You got that?
So this would happen even without pollution and all that stuff,
Yes.
right?
There would be a lower density of ozone that it would occur there regardless of human activity, because there is chlorine in the atmosphere. Yeah. Now, us pumping more into the atmosphere is not helpful, and that's why we're trying to stop.
I was just going to say, what is the difference between that, like, natural ozone pollution and, like, pollution from us?
Between ozone depletion or ozone pollution?
I don't know, whatever.
This happening?
Naturally, yeah, the ozone depletion.
Well, I think it's just the level. There are more chlorine-containing compounds in the atmosphere because of human activity. But not all of that chlorine is available to catalyze the destruction of ozone. It's just when it's released from those compounds. But those polar stratospheric clouds, the ice crystals catalyze the release of the chlorine, and so then you get this problem. But then when the crystals are gone, the problem goes away. So I think this is a really interesting example of catalysis and reaction mechanisms and stuff, and how this is important to real life, right? I am not going to test you on ozone depletion, okay?
We should
So,
go up there and collect the crystals.
yeah. Well, I'm sure if you did an internet search, you could find papers and articles with more details about this. And I have all kinds of questions like, well, exactly how did they figure that out and stuff like that. Okay, on to something a little more down to earth. The reaction between ethene and hydrogen is slow at normal temperatures. So ethene is got 2 carbons with a double bond. And this can react with hydrogen to form ethane. So this hydrogen molecule, 1 hydrogen is added to each carbon, and that double bond is broken. But it's slow. If we have finely divided platinum, palladium, or nickel, that catalyzes the reaction and causes the reaction to occur quickly. The large activation energy of the original reaction, because of that hydrogen-hydrogen bond, is lowered. So we can use this as an example of the 4 steps of heterogeneous catalysis. The first step is adsorption. So here we're talking about, we have reactants in the gas state, and the catalyst is a solid. So the reactant has to stick to this metal surface. And then diffusion is where these reactants can move around on the surface until they approach each other. The reaction is where the reaction actually occurs, and then desorption is where they leave the surface again.
Does it have to be a solid for it to absorb?
To have adsorption, it has to be a solid, yeah. I suppose there were liquids. You could have liquids, but we're going to pretend that doesn't happen. Yes?
So I remember from doing Bohr-Haber cycle that there has to be ionization energy, or atomization. You got to break that bond and then ionize it.
Mm-hmm.
How does a catalyst break apart a hydrogen bond?
Well, that's an excellent question. Why? So basically you're saying, why does this catalyze the reaction, right? How does it do that?
Well, how I can see how by the adsorption, diffusion, reaction.
Yeah, but when this adsorbs, why does that lower the activation energy? Well, I think when we talk about enzymes, it's a similar idea, but it's easier to explain. So in living organisms, most of the reactions that occur, and there's like gazillions of them, that's biochemistry, most of those reactions are too slow to allow the organism to survive. And so we need to make them faster, but you can't just increase the temperature, right? It's like, well, that reaction will go fast enough if we put you at 150 degrees Celsius. Yeah, but then all kinds of other really bad things happen and you die anyway, right? So enzymes are biological catalysts. They're actually just large protein molecules, and they have an active site where the reactant molecule, which is called the substrate, binds, and then the reaction occurs, and then the reactant leaves that active site, and the active site's available for another reaction. So these greatly reduce the activation energy of the reaction, and they speed things up. So this is the general idea here. So we have the enzyme plus the substrate, and this binding happens quickly. It's a fast reaction. So the substrate binds, and it could leave again without undergoing any reaction. The substrate binds, and oftentimes then it will react. So here it's breaking into 2 products. This is the slow step of the breaking into 2 parts, and that's where the enzyme causes that to go faster. These enzymes typically only react with or work for one reactant. They're very specific. So it's only going to catalyze a single reaction. But the substrate comes in, the reaction occurs, and then this active site is ready for another one. So let's look at how this works with sucrose. In order for you to metabolize sucrose, it has to be hydrolyzed. So what happens in hydrolysis is sucrose is actually two sugars bonded together, glucose and fructose, and in order to metabolize this, we have to separate it into the two individual sugars. So we need to break this one bond right here. At body temperature, that happens really, really slowly, and so we wouldn't be able to use sucrose. Sucrose is table sugar. But what happens with the enzyme, it's called sucrase, when the sucrose binds to this active site, and a lot of this has to do with hydrogen bonding, it comes in here and it fits into this active site in a way that puts some strain on this bond. It strains it. It's like everything else is fitting really well. If we just kind of stretch this one bond, then all these other great things happen. And so this bond is weakened. And so then it's much easier to break. And so the reaction goes much faster. And so that's the same idea that's going to happen in other catalysis. But here I can tell you exactly what's happening. It's the straining of that bond that needs to break. Any questions? Yes?
Can we assume that even without the catalyst, the bonds would break just at a much, much slower rate?
Hydrolysis of sucrose would occur, but at a very, very low rate. Yeah. Definitely not useful. So enzymes are very, very specific. They catalyze only a single reaction. They speed those reactions up by factors as large as 1 billion. So it can make a reaction go 1 billion times faster. That's huge. Things that inhibit enzymes are typically very toxic. So if your sucrase was bound up with something else, and some of these inhibitors will bind irreversibly to the active site, so you fill up all those active sites, then you can't metabolize sucrose anymore. And that can be extremely damaging to an organism. So, of course, if you want the thing to live, you want to avoid that, but it can also be really useful if you're trying to kill insects, right? If you find this enzyme, or maybe you're trying to kill a virus.
Can you kill
Maybe.
a virus?
Well, this is one of the ways that they're fighting the AIDS virus. You can't actually kill it, but you can inhibit it to such a level that it can't reproduce. And so it's still there, but as long as you keep inhibiting it, it's at undetectable levels and has no effect on you. So that's as close to a cure as we've gotten, but it's pretty awesome that we can do that. And the study of biochemistry, you learn a lot about how your body can turn enzymes on and off, right? And so it can switch this on when it needs, to do something with your insulin, and then it can switch it off. And so it's this whole series of control gates, basically, controlling this reaction, that reaction. And it's just us walking around being ourselves.
And if those enzymes don't work or don't lock us, typically when you'll see people that have like intolerances to certain foods, like people with gluten intolerance, they lack that
Right.
enzyme that breaks it down.
Yep. And lactose intolerance, that's very common in Asians. So there's a lot of, we had a birthday party for half my kids last night, and we had ice cream cake. So before they ate the ice cream cake, they passed the lactate around. Here, how many are you supposed to take? Take 3 of them. Okay. So they all ate ice cream, and today they're all still fine. But as a baby, you're able to break down lactose, which is the sugar in milk. But then as you mature, especially if you stop drinking milk at some point, your body says, oh, well, we don't need to make this anymore, and it kind of forgets how, and then you're done. But you can always take some some lactase with your lactose, and if you do it right, it'll come out just fine. But you can have a lot of genetic defects. If your body is lacking the enzyme needed to do a certain task, that can cause a lot of problems. Phenylketonuria is one example where you can't process phenylalanine. Phenylalanine is a naturally occurring amino acid, and so that's kind of a problem. But it's also something that's produced as a product of the metabolism of NutraSweet, aspartame. And so people who can't metabolize phenylalanine should definitely not eat any aspartame, because that's going to increase that problem with them. They have to also limit their diets to limit the amount of phenylalanine that they ingest.